Welcome back to another Mateo Valley Calculus tutorial. Today we'll be learning about Euler's method. And Euler's is basically a way to approximate the value of a function when you only have its derivative and an initial condition. So let's start off by doing an example problem. So let's just say that dy dx is equal to 5x squared minus 6 over y minus 2, with the initial value of -1 is equal to -4. So those are the two requirements for using Euler's method, which is you need to have a differential equation and you need to have an initial value. So let's say that we want to evaluate f of 0 with this. What we would do is we would use the formula for Euler's method, which is the new y is equal to the old y plus the dy dx of the point of the old point times the change in x. So what this means is that you have an old y, you have an old function value, and you're multiplying it by the slope at the next point. And when you do that, you're basically adding it to the old y, which would give you the new y of the actual function. It's always going to be an approximation. For Euler's, the answer is never actually going to be the true value of the function, except for the initial value. So with this, we would start off by using -1, comma, -4. So the new y will be equal to the old y, which is -4, plus, then we plug in -1 and -4 into here. So when you plug that in, you get 5 minus a -1. And since we want to evaluate it from -1 to 0 with 2 steps, we would have to use a step of 0.5. So that means that the delta x would be 0.5. So now the new y would be equal to -1. So now we have our new y, and since we want to move up half a step in the x direction, our new point would now be 0.5, comma, -1. So the new y would be equal to -1 plus, so when you plug in 0.5 in here, you get 0.25 over 5, so that's 5/4, minus, and then 6 over 3, which is just 2. So, and all of that also times 0.5. So when you simplify this, you get that the new y is equal to -1 plus 13/8. So the new y can be equal to 5/8. So that's the answer for this equation. So basically what we did here was, with Euler's, let's just say we had a curve. And we had the derivative at these points, but we didn't know the actual function values. So we approximated with a sort of linear approximation. And then we took this point, and from there we approximated with a new linear approximation. So the problem with Euler's is that an error will always be compounded the farther away you go from the initial condition. So that answer might not be the exact answer of the function value for that differential equation, but it's relatively close since we stayed near -1.